Hello, this is my presentation for physics. The purpose of this presentation is to introduce thermodynamics, which is a part of physics that deals with dynamics of thermal phenomena, hence the term thermo, which means heat, and dynamics, which means force. I'm going to talk about the basic principles of thermodynamics, which is the first law of thermodynamics, and I'm also going to talk about thermal conductivity and specific heat capacity, which are the physical properties of every material object. I'm going to use these lab equipment to conduct some experiments that will kind of illustrate the theoretical concepts in this presentation hands-on. Ancient Greeks were the first to ponder on the nature of matter. The very word atom comes from the Greek language and it means uncuttable or undividable. Democritus, a Greek philosopher, is the author of the atomic theory that says that all matter is built from fundamental, indivisible components known as atoms, a theory that is held to this day by science. However, it was more than 2,000 years later, in the Age of Enlightenment, that brought significant advancement of our understanding of matter, the nature of heat, and energy in general. One of the theories in those times was the caloric ether theory of heat, which was proposed by the genius French chemist Antoine Lavoisier, who was unfortunately executed on the guillotine during the French Revolution. According to this theory, there was a weightless, colorless, and invisible fluid moving from a hotter to a colder body. Despite better ideas circulating in scientific circles at the time, this theory prevailed and was even useful to a French officer and engineer, Sadi Carnot, who improved steam engines and invented the perfect engine, an idea that is used to this very day to measure the efficiency of engines. Eventually, the caloric ether theory proved to be wrong by Benjamin Thompson, better known as Count Rumford, who wedded Antoine Lavoisier's widow, who was also a great scientist woman in her own right. Thompson, he conducted various experiments with cannons, boring holes in them. At one point, he got an idea to submerge the cannon underwater, and he managed to get the water boiling during the process of boring. He showed that the mechanical energy, in this case drilling, produces heat, in this case friction. And there's not the movement of any mysterious, invisible caloric ether agent. This was the beginning of today's understanding that heat and work are interchangeable and are closely linked to properties of the materials used in the exchange between said heat and work. Today we understand that thermal energy, known as heat, is actually a form of kinetic energy released by the motion of atoms bumping against each other. The more atoms jiggle, the more energy they have, which causes the higher temperature. If atoms vibrate fast enough, it can cause matter to turn into a liquid. And atoms can even move so frantically fast that it can even cause matter to change into a gaseous state. Water is easily observed in our daily lives to go through these stages. Ice, which is a solid, water, which is a liquid, and water vapor, which is a gas. However, even metals like gold can melt into a liquid, and in extremely high temperatures, it can even change into a gas. Now we can formulate the first law of thermodynamics. In fact, the first law of thermodynamics is a version of the law of conservation of energy, which was first formulated by a great scientist woman, a very underappreciated scientist woman of her times, Émilie du Châtelet. She postulated that heat is the effect of internal motion of the particles of all bodies, and that the total energy in an isolated system remains constant, although it may be converted from one form to another. Or in another way, energy is never lost, only changed in form. From this, it is easier to derive the conclusion about the relationship between internal energy, heat, and work, which comprises the first law of thermodynamics. Change of internal energy, delta U, equals energy transferred as heat, Q, minus work, W, done on or by the system. All these quantities are measured in units called joules to recognize the contribution of the English physicist James Joule. Solids, liquids, and gases all expand with increasing temperature. This phenomena is used to build thermometers, like this one. Inside of a thermometer, there's a thin closed pipe filled with colored alcohol, and this liquid changes its volume. It expands and shrinks, rises and falls inside of the pipe when there is a temperature change. Now I'm going to demonstrate the thermal expansion of a metal object. Although the effect of metal changing its volume with changing temperature may not be super spectacular, we can observe it using this device. Here I've got a brass ball suspended on a chain and a ring. The diameter of this ring matches the diameter of the ball exactly, so the ball fits in snugly and passes through comfortably. However, when we heat this ball up, something interesting happens. Now the ball doesn't go through the ring, which means that the ball has increased in its volume. Cooling this ball down will help bring it back to its original size. Different metals conduct heat differently. It's similar like with electricity. Some materials conduct electric energy better than others, and conversely, some materials conduct thermal energy better than others. So here I've got 4 different metals attached together, which forms a cross. And the metals are aluminum, copper, steel, and brass. I stuck these cork chips on the end of the metal strips using candle wax. Now I'll heat this up and see what happens. As you could see, the cork chips fell off at different times, signifying the difference in time that the temperature had reached the melting point of wax. Unfortunately, this experiment didn't really go the way I expected it to, because apparently copper is the best conductor of heat, but in our case, the cork chip on the aluminum fell off first. And, there are many factors that could have come into the fail of this experiment. Like, let's say I failed to put all of these cork chips at the same distance from the center on these metal strips, or I could have, maybe when I was moving this gas burner, I heated up the right more or the left more. Nevertheless, we can still see that the metals conduct heat differently, as the cork chips did fall off at different times. Maybe not to my expectations, but they did fall off at different times. What if 2 metal strips are fastened together so that they cannot slide relative to each other. What happens when they start to expand at different rates with rising temperature? I'm going to heat this up across the length evenly above this gas burner. As we can see, this setup has bent, and this happens because one metal expands faster than the other, and it creates tension, which causes this bimetallic strip to bend. This effect is used in devices such as thermostats as switches regulating heating and cooling. Another use is in electric circuits where they cut off excessive currents. Every material possesses a characteristic feature called specific heat capacity, which describes how well it conducts heat or how well it absorbs and stores heat energy. We measure this property by the amount of energy, joules, needed to heat up 1 kilogram of the substance by 1 degree Celsius. For example, the specific heat capacity of water is 4,200 joules per kilogram per degree Celsius. We can write this formula as follows. In order to heat up 1 kilogram of water for 1 degree Celsius or Kelvin, we need 4,200 joules. And that's the specific heat capacity of water.